Good morning, everybody. This is Jenny Hellrung with the ASQ Statistics Division, and we have a great webinar for you today on Quality 4.0 and data science. Our lecturer today is Dr. Cotter, who is a master lecturer with the Engineering Management and Systems Engineering Department at Old Dominion University. He has a PhD in Engineering Management and Systems Engineering from Old Dominion University, as well as a Master of Science in Engineering Management from
UMass Amherst.
Yep, at Amherst, and also an MBA with a finance concentration and a Bachelor of Science from the University of South Carolina. And he is certified in quality and reliability by ASQ. He has over 40 years of experience in engineering management and in automated chemicals manufacturing, computer manufacturing, and defense electronics. He's supported projects for the startup of production facilities and a research and development center. He has managed Lean Six Sigma projects, automated quality information systems, and automated measurement systems. So we have a well-qualified speaker today, and with that, I will turn it over to him. Thank you.
Okay. Thank you. I want to welcome you to the ASQ Statistics Division webinar on Quality 4.0 Data Science, the Variance Components Problem. As she said, I am Dr. Steve Cotter with Old Dominion University. This discussion, this is the qualifier, represents intermediate results from my research into the impact of Industry 4.0 cyber-physical systems on Industry 3.0 automation, productive, and quality systems. We're still in that transformation, and there's a lot of uncertainty on impact. Our discussion today, first we'll look at the current Quality 4.0 data science research, then establish the foundation of Industry 3.0 products, service design, variance, components. Then we'll add on top of that, later on top of that, the Industry 4.0 service design, variance components, and finally end with my definition, and I'm qualifying that as my definition of Quality 4.0 data science, design, variance, components problem. And for me, this is a much bigger problem than data science is, traditional data science has approached. And if you have any questions, just ask. How do I get, is there a chat here on WebEx? I'm used to Zoom.
Yes, yes, please ask your questions in the chat, and we will read those off at the end of the presentation.
Okay, good. Okay, so current Quality 4.0 data science research. Data science, by definition, is a scientific study of data to gain knowledge and solve problems. This is kind of a generic definition that occurs in a lot of disciplines, particularly related to Industry 4.0. The main problem with data science is the extraction of meaningful insights from pattern discovery in massively large data sets for business decision making. And then for Quality 4.0 data science, just replace the words business intelligence with quality intelligence. The data science life cycle has 7 sequential steps that repeat cyclically. First is business understanding, identifying the key business strategies and metrics, the context within which the data science is to be applied, data mining, data analytics. Second step is data mining, that's discovering information patterns and massively large data with respect to those key business metrics. Once you have representative patterns, data cleaning is next, just the process of fixing or removing incorrect, corrupted, incorrectly formatted, duplicate, or incomplete data within an assembled data set. Step 4 is data exploration. It consists of 3 steps. Describe the data characterizations such as size, quality, or quantity and accuracy to understand the nature of the data itself. This is the called meta-analysis in data analytics. Exploratory data analysis isolates patterns and features of the data and reveals these forcefully to the analyst. This is the Tukey approach to exploratory data analysis. Once you have a hypothesized model, you confirm that through confirmatory data analysis to assess the reproducibility of the identified patterns or effects in the data. Oh, next, once you have a model, feature engineering is a process of transforming raw data into relevant information dimensions for use by machine learning models for creating predictive models. That's where we've been going all along in data science. The predictive modeling is selecting the best or best set of stochastic model or models that can be applied to predict business metrics based on feature dimensions in the data. And typically, predictive modeling is some kind of classification, clustering, forecasting, examining outliers, some kind of time series dynamics. And then finally, step 7, data visualization, the representation of data through the use of graphics such as charts, plots, infographics, and animations provide an easily understood summary of predictive model results. This is where we output to management, and we want to assure that management understands what the statistical model is telling them. Okay, so with that, I find, or at this point in time, based on my research, data quality 4.0 data science is the direct portion of general data science principles from business analytics or business intelligence, principles and method into quality systems. And typically, I've found that there's 2 approaches. One is replacing statistical quality control with predictive quality models, that is leveraging big data, industrial big data, Internet of Things, and artificial intelligence to solve new range of intractable engineering problems. And the second is integrating AI and machine learning into experimental design and process improvement. Now, both of these are admittedly important research areas, but from my research, I feel that they both ignore the looming Industry 4.0 horizontal vertical integration problem. And if you want, I have these articles and give you complete references to these articles. So Industry 3.0, 4.0 products, service design, variance components are baseline, because that's where we were in the last half of the 20th century. First of all, definition, customer user experience quality is the y equals f of x z, where x is the controllable variable, z are either predictive or non-controllable, x parental variables are covariates. But anytime we make the y equals f of x conversion, we implicitly have those z covariates that result in the true functionality behaviors transformation. Now, the definition, the 8 dimensions of quality are found on the ASQ website, well published, come from Garvin's work, 1984. He noted that quality had been defined at that time from 5 traditional approaches. One was transcendent. This is some idea of excellence. 2, product-based, product differences. 3, user-based, attributes, services capable of fulfilling customer needs and wants. 4, manufacturing-based, meets specifications or doesn't meet specifications. And 5, value-based, the degree of excellence per unit price. Garvin argued that the different approaches led to differing views of quality. Garvin argued that we need to view quality from the design to market perspective, and from that he developed the 8 dimensions of quality as a logical consequence of that design to market perspective. Published his original paper in '84, and I think, if I recall, it was either later in '84 or '86, published another paper competing on the 8 dimensions of quality. Those dimensions are performance. This is the intended y equals f of x functionality behavior. That is what we seek to design and seek to deliver. I use the term functionality to differentiate what we can control as designers in terms of what the end product actually does versus behavior, what it does in use in the customer's environment. That's what the customer wants, and quite often that what we deliver, the y equals f of x functionality, is only an approximation of the true behavior that the customer needs in his end-use environment. Reliability, that's the failure rate in use, how long performance, the y equals f of x functionality behavior actually performs to failure. Durability, product lifetime. Serviceability, ease and timeliness of product repair. Aesthetics is subjective product dimensions. I like to reference my wife and I. Last time we went looking for a car for her, she was looking at the color combinations, whether or not she liked the dash layout in terms of ease to read. I'd already been online looking at the miles per gallon, the repair cost, all of the technical aspects. Features, these are competitive satisfiers. A few years ago, before it was mandated by law, backup cameras were a competitive satisfier. Now they're a part of every vehicle. Like I think probably the big competitive satisfier now is the LiDO image of the entire vehicle with the surrounding environment. Perceived quality, this is the organizational reputation. It sometimes biases the preceding 6 dimensions of quality. And then conformance to standards, these are industry or governmental standards, particularly in Europe, where Europe has a lot more product standards. For service quality, I go to Verschuermann, Zeltams, and Berry's 1988 development of the ServQual instrument. That was they validated a 22-item instrument to assess service customers' perception of service quality. The 5 dimensions across the 22 items were found to specify service quality consistently. Those dimensions are responsiveness, promptness, and helpfulness of service. I like to use the restaurant experience because we all do that. You walk in and your waiter is immediately there, seeking to if you need water, if you're ready to order, etc. Professionalism, knowledge and skills of the provider. Going back to the restaurant, my wife occasionally likes to try something new, and she'll ask, "Is this good?" Well, at that point, if in the higher end restaurants, I say higher end, they've usually been exposed to all of those, and they can tell you, yeah, it has these ingredients in it. If you like it is, I like it, or I personally don't like it, but they have the knowledge and skills to describe the product and itself. Attentiveness, this is caring, personalized, addressed customer needs. Reliability, every time you return, you get the same level of responsiveness, professionalism, and attentiveness. Intangibles, this is the physical features and appearance of the service facility and personnel. Additionally, in Industry 3.0, stability, capability, and robustness are fundamental concepts in quality control. We've used the term stability for years. Capability, of course, we all know about CP, CPK, and robustness is some concept of signal to noise ratio going back to Taguchi's introduction. Stability is used rather loosely in terms of some idea of set point with random variation. So for this work, I define stability or capability in terms of the y equals f of x transformations. For stability, And I'm partially taking this from quality and partially taking it from feedback control theory. So a process can be set at a design y equals f of x set point. This is a design point, and it will remain at that set point with only expected inherent variations, i.e. the residual variations are normally distributed with mean zero and some constant variance. Capability, stable process is capable when its natural tolerance limits, typically the plus or minus 3 standard deviation limits for normally distributed errors, although they don't have to be normally distributed, and you can develop process capability indices for non-normal processes are strictly less than the design specification limits. Robustness, a y equals f of x, now I'm including the given z parents, unmapped or uncontrolled parents, and covariates. Process is insensitive to x predictor variation and z covariate disturbances. This is getting back to Taguchi's idea of mean versus signal to noise. That brings us to design theory. The design degrees of freedom recognizes the y equals f of x Bayesian nature of product and process service design. Design degrees of freedom are the number of X matrix controllable input variables plus the Z vector of matrix of non-controllable input variables. Those Z covariates are in the form of other. I'm going to use the word non-decomposable X parent, non-controllable X's, parental dependencies of the X controllable variables runs through ZJ covariates that exist in all but the simplest frameworks of product designs. And by frameworks, I'm referencing level 1 of Boulding systems hierarchy, because most of Industry 3.0 products were in the frameworks or clockworks, and then when we got into more sophisticated design, we had the feedback control. The conditional parental or Z covariance dependencies induce moderating or mediating parental variables are covariate feedback loops that inhibit the y equals f of x bijective mapping and design control. We'll come to the bijective mapping part in a little bit. That was assumed in the y equals f of x Six Sigma representation of the transformation. And it was also assumed in Suss's axiomatic design. The control degrees of freedom, though, are the number of X matrix controllable input variables. They're representations that are taught in axiomatic design in Six Sigma programs. For Industry 3.0 products and services, the y equals f of x transformation is implied fully decomposable, single input, single output, multiple input, single output, or multiple input, multiple output. Now in the latter, we assume that the y's are independent and they depend on a common set of x's. By independent, they don't interact. Suss 1990 dependence and minimum information axiom. And this is ideal in the limit design decomposition results in y equals f of x bijective design control maps admitting Suss 1990 axiomatic design independence and minimum information axioms. Note that the design on the left results in a one-to-one bijective yi equals f of xi, single input, single output mapping for each yi functionality. The design on the left, on the right, results in a many-to-one surjective yi equals f of xi, multiple input, single output mapping for each yi functionality. This is typically the y equal beta O. On the right is typically the y equal beta O plus beta 1x1 plus beta 2x2 plus beta 3x3 plus the residual error term. all of those being different for each yi output. Many to one surjective vector yi equals f of xi, multiple input output mappings or multiple output mappings are possible if and only if the vector yi are independent and functionally dependent on the common xi control variables. That's not depicted here. But for instance, y2, y3 might be commonly dependent on transformation of x3, x4, and x5. And then y2, y3 could be independent themselves. In all but the simplest Industry 3.0 frameworks, products, and services, non-decomposable functional control variables and covariates, the non-decomposable control variables are the right columns, and the overlapping yi behavioral variables, the bottom rows, are typical. Independence and minimum information cannot be attained due to the y equals f of xz feedback loops created by the non-decomposable functional control variables and overlapping yi behavioral variables. Note this, note that the right column again contains the z covariates in the form of other non-decomposable experimental dependencies on our true non-controllable CI ZJ covariates that admit moderating and mediating feedback loops. The overlapping yi behavioral variables in the bottom rows induce feedback through the yi yj interactions. Again, this was all out of design literature. The second source, so we've established the part of the design problem from Industry 3.0 that carries over into Industry 4.0, and that's from the induced feedback loops from the non-decomposable functional control variables and the overlapping yi behavioral variables. Moving on, the second source of performance variance and instability in Industry 3.0 products and services arise from the feedback control design. Now, this is if you from the feedback and feedback control literature, there are a number of representations, but this is the closest representation to the y equals f of x transformation feedback control loop in quality systems. And I've depicted it as a typical single input, single output, multiple input, or multiple output, or single output, multiple input, single output, or multiple input, multiple output, and the latter assuming the yi independence in that case. Quality control feedback loop set in control theory transfer function terminology. That's why we have the S's because we've made the Laplace transformations. And Laplace, for those of you who recall your undergraduate control theory, the Laplace transformations make it easy to additively determine the properties of control, which are stability, performance, and robustness. In this case, dy on the left-hand side of the screen is the reference set point. ds is the feed-forward controller with time-dependent dt output. xt are the system inputs. These are the f of x, the things that we want, the inputs that we're going to transform into some output functionality. The integration of dt, xt, and hs feedback at the integrator point here produce the resultant et control. That's fed into the control actuator CS, resulting in control action UT. There. Are we seeing my cursor, or am I just waving the cursor around for fun? Feedback from host?
We can see your cursor.
Okay, good. I hate to be talking long and somebody say, well, we couldn't see that. Okay. The important part right here, this is combining control theory, which looks only at gain, either log gains are frequency gains. And this is where we get the y equals f of x transformation. So I'm combining that, and notice that we have the ZT be directly uncontrolled into the g f of x transformation. So that results in actually y equals g f of x given zj Bayesian dependency in the xt output. Then finally, measurement error M is independent additive variance components error due in the result of yi product process or service behavior. In this case, note that the term that the yi behavior is used in this discussion to differentiate between design f of xi functionalities and end user experience yi product process or service behaviors. The error term in the y equals f of x given z plus error reflects the difference in design functionality and end user experience functionality. From design theory, as in control theory, it is in the error term where the real engineering design takes place. We can get useful models that are close in terms of functionality that may approximate end user behavior, but in reality, it takes designer experience and some tweaking to ferret out that error term and develop a product that is as close as possible to the functionality behavior requirements. Feedback control gain and frequency gain are both related to the overall gain of the system. That's the g f of x given z, which determines the feedback control and performance stability robustness trade-off. The gain HS, now to go back to gain, this is our feedback control through the feedback loop. The feedback path is a function of frequency. In linear time invariant control systems, design feedback gain is calculated to minimize the quadratic performance index J while ensuring system stability. So we have here a typical state space representation of a system minus the dt in the yt equals cxt. There is often a or shouldn't be. There can be a plus DUT error term, and that allows the input error to directly feed through to the YT. But this is typical state space, so it's without the plus DUT, it's more of a deterministic representation, which allows simplification in development of control theory. The quadratic performance index J is Y transpose, the transfer S, Y transpose. And for those of you who recognize that from matrix algebra, that's your quadratic term, plus the integral TO to TF of YT, QT, YT, or sorry, Y transpose QT, YT, another quadratic term, plus the UT input gain, UT, or U transpose gain U of the transformation. Of course, S is a quadratic in CT SYC, or C transpose SYC, and then QT is likewise, our QT is the C transpose QYTC. So again, in feedback control gain, we are minimizing, we're using something similar to least squares to minimize the error term and maximize the performance or the gain. Frequency gain, the gain of the transformation function gf of x, which is also a function of frequency. Increasing the gain shifts the gain frequency plot upwards across all frequencies. However, the trade-off is it decreases system stability. So there's our stability. The higher the gain of the system, the more efficient and effective the G or the G f of x given z transformation. the decrease in system stability. So here we get off in design of control, or get on to design of controlled systems, another trade-off. So this is the performance stability trade-off, which can be determined only through some level of design, control system design, trial and error, to differentiate it from the control or design of product y equals f of x characteristics. Robust stability in a control system is the control system's ability to remain stable despite uncertainties in the f of x given z plus the error response, i.e. the system being stable over the entire family of gain processes. Note that this is a typical Nyquist plot for system robustness. The key here is the around the -1, there is a unit circle of instability area or instability area. And the idea here is we want to set the gain such that the x given z control point is far enough away from the non-robustness or instability area so that there's no overlap, there's no probability, or the probability of overlap goes to 0 at this point. We definitely do not want to set the coming down the Nyquist curve here, the f of x z point inside the non-robustness area. So we have to have an error allowance for the f of x set point such that the C delta R critical region does not overlap the non-robust critical region. So the next concept we need to come to is basic or bounded input, bounded output stability. A feedback control system on slide 16 is, I'm just going to use the term BIBO, stable if for every system input, the output YT is bounded. Again, another fundamental concept from feedback control theory. We also have something called interconnected bounded input, bounded output stability. And this is a set of so we can take, we take a set of BIB feedback controllers each. They are stable and robust. So in a set of interconnected BIBO feedback control systems is interconnected BIBO stable if each feedback control system is internally asymptotically stable, two different meanings. One is a point in time, and one is as time goes to infinity. And the interconnected system transmittance, key term there, the interconnected system transmittance is also BIBO stable. Note on this slide that BIBO stability of single input, single outputs can be extended to MIMO systems if and only if the gain G is absolutely integral in the area of 0 to infinity. This means that two or more interconnected BIB control systems can result in unstable systemic performance or unstable systemic IB interconnected BIBO operation if they are not absolutely integrable. So it is possible to design individual controllers that are BIBO stable, interconnect them, and then the interconnected controllers system transmittance will not be BIBO stable. So there's the connectivity problem. Interconnected BIBO control systems must have compatible input-output dimensions. If not, they cannot be interconnected. The interconnected BIBO problem, it has been demonstrated in control theory that two similar stable BIBO control systems, when interconnected in sequence or parallel, may not yield optimal performance or be jointly stable, i.e. the joint system transmittance is not BIBO stable. So summary. The y equals g f of x, combining the feedback control theory and the Six Sigma f of x, y equals f of x, plus variance errors are induced by one, non-decomposable y equals f of x parental and covariant feedback loops. These are possibly unknown, and those are from the non-decomposable overlapping y's and x f of x redundants or x redundant design feedback loops. Feedback control performance stability, robustness trade-offs, an interconnected control system in which the transmittance is not BIBO stable. Now there is assumption here, the final y equals f of x. Now I'm doing a sum here, GT or YT. Now the YT here represents the output functionality of the system. So the sum is either for additive systems and the pi product is for multiplicative systems. So product quality behavior is produced by a single Industry 3.0 automation plant combined of some designed internal interconnected BIBO series parallel combination or feedback control transformations. The importance of this assumption is for those of us who have worked in industry, we always get those products that by design should have certain performance characteristics, and when you go to manufacture them, they don't. And that's within the Industry 3.0 four walls, because typically product design was put into chunks, so that if like for instance, automobile manufacturing, before I moved from South Carolina, the BMW plant had a feed from their facilities, so that they only had the interfaces to all the elements to come together to build an automobile. So each facility was building a unit of performance that then was combined into the final unit of performance. And that's one of the differences between Industry 3.0 and Industry 4.0. So hence, for a single plant process, the Industry 3.0 product performance variance components can be written here. I'll just step through each one. The end product variance yi is a function of the sigma square dx. That's the decomposable x variances. Sigma square nz, non-decomposable z variances, covariances. Sigma square sub st, stability variances. Sigma square GN, gain instability variances, sigma square NR, non-robustness variances, and then finally the reproducibility and repeatability measurement errors. In the foregoing single plant process, the product variance equation implies the following product quality design matrix, in which the design objective is to minimize the difference between the variances, realized variance, functionality variances, and the designed f of x transformation variances. It implies block matrix design. Okay, so now we've established Industry 3.0 variance components. Next question is, what are the variance components induced by the Industry 4.0, 5.0 technologies? Industry 4.0 is an evolution of Industry 3.0 automation. I use the word asymptotically because we are in a transition at this point in time, and it's questionable by industry as to how close we actually achieve full vertically and horizontally integration, or vertically and horizontally integrated distributed manufacturing. So Industry 4.0 is the evolution from Industry 3.0 automation asymptotically toward horizontally vertically integrated distributed manufacturing that is planned, executed, and controlled by artificially intelligent cyber-physical systems using cognitive computing over Internet of Things, cloud computing. There is the big difference in the limit. Humans are out of it, out of the system, and at any point in time, a downstream production can negotiate some combination upstream production for ideally the best performance at the lowest unit cost. And humans and the limit are out of that collaboration. So the goal is intelligent distributed manufacturing, where the most capable, efficient combination of y equals f of x transformation processes can be negotiated at any instant in time. And this is a limit definition, not a norm definition. Industry 5.0 constrains Industry 4.0 horizontally, vertically integrated cyber-physical manufacturing to achieve the most capable, efficient combination of y equals f of x processes that support the evolution of a human-centric, resilient, and sustainable society. Those are the goals of Industry 5.0. So Industry 5.0 is more of a realignment of Industry 4.0, distributed cyber-physical production efficiency, to broader societal outcomes than it is an industrial revolution. Industry 4.0 goal of horizontally vertically integrated distributed cyber-physical manufacturing means that product design matrices, slide 15, and their associated variance components, slide 24, will also be distributed across horizontally vertically integrated distributed manufacturing processes. So my question, and this is not just my question, I actually ran across this question in some calibration literature: what additional variance components will be induced by horizontally vertically integrated distributed manufacturing? For Industry 3.0 products, processes, and services, all of these additive designs or multiplicative dy functionality design was designed and y equals f of x built into the physical products or service end user use y behavior. If the end use behavior had to be changed, the design knowledge either replace or revise or replace the physical dy design functionality came from external human sources, i.e. we redesigned it and then reintegrated it. So it was kind of a stop, redesign, come back and integrate it into the existing design. So we need to differentiate Industry 3.0 fixed functionality variance components from Industry 4.0, 5.0 smart products, processes, and services dynamic variance components. So we need a definition. Smart product, and this again, my definitions. I'm looking for peer review and feedback, others interested in this research on the impact of Industry 4.0 technologies on the transformation from Industry 3.0 technologies. My definition of a smart product is a digitized cybernetic physical design realization with horizontally, vertically, Internet of Things connectivity to external digitized smart entities and human entities that self-enhances. Key term here is self-enhances. It's additive or multiplicative functionality designs resulting in the y equals f of x system behavior performance within a system of systems smart products. Key point here is the word self-enhances. That differentiates Industry 3.0 products from Industry 4.0 or Industry 4.0 products from Industry 3.0 products. Self-enhances means that smart products, one, have the initial designed in self-knowledge of how to detect deficiencies in current self-functionality and self-design new functionalities, and two, have the initial designed in capabilities to acquire the information, energy, and resources to self-produce new functionalities. Current AI research focuses on the first enhancement, but leaves the second self-production to external human capabilities. Smart process is digitized cybernetically. So this is a smart product. Smart process is a digitized, cybernetically controlled. Now we're down to the PXI that results in functionality of XI. So we're at the transformation process. It's at the transformation point in the process itself. Again, with IoT connectivity to the smart products, it transforms into external digitized smart processes and sensors to human entities that self-enhances, that word again. It's PXI, FXI, system transformation within a system of systems, PXK, FXK transformations. Key point again, in addition to self-knowledge and self-production, smart processes are smart products themselves. Smart processes self-enhancement requires the initial designed-in abilities to detect and communicate with other smart processes and detect and communicate with the smart products it transforms through sensors over the IoT. The ideal future production is as a smart product is being produced, it can communicate with this process about its functionality that's being induced by the transformation. Smart service is a digitized, cybernetically controlled PXI, FXI service transformation that uses data and information gathered in smart products via IoT connectivity and human entities via sensors to self-enhance. That word again is delivery, or that modifier is delivery of expected systemic, functional, and technical performance and reliability within a system of systems of smart services. The common term for all Industry 4050 smart products and processes and services is self-enhancing. Industry 4050 have self-designed, additive or multiplicative knowledge and intelligence functionality built into their original design, and PXI, FXI transformation capabilities necessary to self-organize. That's part of being a system of systems, to evolve that self-organization internally and to co-evolve that self-organization with other co-evolving smart products, processes, and services. New revised and resultant YJ equals F of XJ system behavior performance with respect to system of systems set of PXK, FXK transformations. The ability to be self-enhancing implies that smart products, processes, and service initial design must have non-decomposable feedback control dependency relationships, going back to our Industry 3.0 design matrices, necessary for self-organization, evolution, and co-evolution. That has to be built into those margins. This implies the following additional variance components: Yij equals sigma square Yij equals sigma square Yi. Sigma square Yi was previously defined as the total sum of Industry 3.0 variance components. Now, I should have said this earlier back at the previous slide. I'm using the random effects variance components representation here because that allows complete testing of all main effects, two-way interactions, three-way interactions, etc. Like the same can be said if we transform these into fixed effects components, variance components. All of the main effects interaction terms can be tested for significance. The typical case is probably going to be the mixed effects of nova variance components. And in that case, we have a further limitation. This is well known in the variance components literature, that given the fixed effects, we lose the full additivity of the random effects, and we cannot test the random effects, main effects, for statistical significance. So that's another limiting design issue here. So that's a caveat. So back to this, using the random effects variance components. Sigma square Yi is the Industry 3.0, and then the sigma square measurement is from Industry 3.0. They were specified on slide 26. Sigma square sub-SO is the self-organizing. Sigma square EV is the self-evolution. Sigma square CO is the co-evolution. And then the sum of sigma square YK states other YK smart processes and service in the production chain. And then the sigma square K measurement is the cumulative measurement error in that IoT interconnected, horizontally, vertically interconnected measurement system. This is where I came on to the problem that's being worked in calibration systems. That is the sigma square sub K mean measurement error. that's in the IoT horizontally, vertically interconnected system, in addition to the production measurement error, sigma square measurement itself. Well, the final question is what additional variance components are contained in the horizontally vertically integrated sigma square YK and sigma squares K measurement system of systems variance components. This is a static representation of what I was just talking about. We're looking at on the right-hand side, the CSI, RSI output to YI is the final step in the production of a smart product, smart service, or smart process. And it's depending on being able to negotiate upstream at any instant in time, or actually collaborate upstream at any instant in time for the best combination of productive y equals f of x production that produces ideally the most efficient and highly customized YI customer behavior output. So in this we have the environment ENV from K to M, and finally the environment. This is both the internet environment and the physical environment. We have the actual IoT transfer, that's the TX. We have the actual interconnected basic input, or bounded input, bounded output problem. And then of course for each selected combination of processes in that horizontally vertically negotiated production chain, we have the performance, stability, robustness trade-off in the control system design. So in the prior illustration, IoT, TX, and RXI are physical information transmission receiver errors in the environment, and the IoT, in this case, the asset administration shell, and the transmission errors induced into the layers of the RAMI 4.0 architecture. I discussed the RAMI 4.0 architecture last year in May, and it's it's really represented here, where we have different layers: the business layer, the functional layer, the information communication integration, then the asset itself. But the key here is in that design, there's an asset administration shell, which is a digital twin of the asset itself, and it translates from the assets language to the RAMI 4.0 IoT language. So that shell, that shell design of that digital twin can induce additional variance components. So this implies the following additional horizontal vertical integration, sigma square YT variance components and associated measurement errors. In this case, sigma square YK, where it was the output, the entire variance components on the previous slide is not sigma square YK. Sigma square YK is the sigma square DS. The variance is due to differences in feedback sensors characteristics. The sigma square DXT variance errors in IoT transmission, sigma square RXK, or sigma square RX is variance errors in IoT receiver, because you have a transmitter receiver, and sigma square D environment is cumulative variance areas by ASS digital twin errors into the RAMI 4.0 architecture. So that leaves, and I apologize, I went back, I shouldn't have. This is an individual set of variance components. So for quality 4.0 data science, we're now in a position to find my definition of quality 4.0 data science, and that is the study of and design of AI-assisted quality 4.0 data analytics for the extraction of, there we go, sigma square YJ, sigma square YI, the industry 3.0 design, sigma square SE, which is the sigma square SE. What was sigma square SE? hang on. And sigma square SE. Oh, that's the environment, sigma square environment, sigma square YK plus the sigma square cumulative measurement error over the IoT and the local measurement error of the final manufacturing point. So this is the total systemic variance components that impact smart products, processes, and services, horizontal, vertical, systemic feedback control of the Y equals F of XI, X given Z, performance, stability, robustness, functionalities, and behavior. So this is my proposed definition of quality 4.0 data science, because the central issue in quality has always been control, stability, robustness, and performance. Questions, comments? I got through 5 minutes ahead. Well, okay, 5 minutes and 30 seconds. Questions, feedback, please.
There's been several questions. I wonder if you could give a little bit of a high level, how you would use this in practice.
How would I, that's the whole point of the research, to answer that question. How do we transition from the industry 3.0 inside a building at a transformation point? Because just about all the quality literature quality literature is at the Y equals F of X transformation. Now we're going to have that Y equals F of X transformation distributed horizontally, vertically. I don't have an answer to that question yet. That is my research.
Okay. Could you give an example of, you talked about the bounded input, bounded output terminology, the BIBO.
Oh,
Could you
yeah,
explain that in a little more detail?
I'd like to, for those of you who have had control theory, let me find that definition. For those of you who have had control theory, that it's a mathematical definition. If YT is bounded, it goes back to basic calculus. If YT is bounded as t goes to infinity, then the system has a unique solution. If it's not bounded, then the system does not have a unique solution. How far along is the software programming in regard to, I didn't get that one, but go ahead. So it really comes down to the definition of boundedness, which really comes out of the calculus of YT.
So is the current software accounting for this?
That I can't answer. That's over on the software side. I'm really, and again, you're talking about the RAMI 4.0. That's a separate research question. I am not sure where RAMI 4.0 is. I know about the RAMI system. I know its architecture, but I do not know the details of the programming. But that's a valid question, because programming a RAMI system is going to have to take into account the variance components, that the additional variance components induced by massively horizontally, vertically integrated, negotiated production systems.
If one wanted to learn a little bit more about this, but maybe starting at a more basic level, do you have any recommendations of where to start?
Yeah, start with the big transformation for me was reading Cyril's book, Variance Components. That's when I recognized that you could describe systems in terms of variance components. It doesn't matter if they're fixed effects, random effects, regression coefficients. Ultimately, all of those can be described in terms of variance components. The problem, the Industry 4.0, 40, or Industry 3.0, 4.0 transition problem is not recognized at this point, and that's the whole purpose of this presentation is to raise the problem and raise the question of what are those variance components, and especially in the case where smart processes have to be self-organizing, self-evolutionary, and self-coevolutionary. No, this is there's probably not a lot of material. If anyone's interested, there's a couple of good articles where calibration is approaching this problem. And that was the seminal insight that I had into the broader problem of Industry 4.0 interconnected VIBO instability, the variance components thereof.
Okay, could you spell the variance components author? You said Cyril?
Oh, English. Cyril. This is just like. Oh, right here. Yeah, I read this book back in the 90s, Variance Components by Cyril
Okay.
Costiella and can't read it, McLaughlin, yeah. So that was where I first got into variance components. And over the years, I've translated quality into variance components, because if you look at quality from random and fixed effects variance components, then a lot of the deviations or the failures in the y equals f of x transformation becomes apparent. So that was the first, but as far as applying variance components analysis to the broader Industry 4.0 massively horizontally vertically integrated connection problem right here. And again, this is a static representation because this can be negotiated dynamically by smart systems, by smart processes themselves. So this static representation should actually be dynamic if I can make it dynamic. But that results in this problem right here. There was another question popped up.
There's some comments about there was great information for you.
What kind of information?
Oh no, they were just commenting it was a good presentation.
Well, it's not that it's a good presentation, it's my research question, my research problem. And I want to put it out, A, to interest other people in the question, and B, to get peer review. Because at this point, it's a highly theoretical question. We have to translate it from theory into practice at some point. But I don't know of anybody else that, other than the calibration community, which there were a couple of articles I read a few months ago that really spurred me to ask this question. The calibration community that's actually approached the variance components of Industry 4.0.
Okay. Yeah, very interesting topic.
Again, thank you. I am looking for other interested parties. I'm looking for peer feedback contribution to my research. This is a much bigger question than I can answer or that any of my doctoral advisees can help me answer. So I'm looking for a community approach to answering this research question. What are those variance components? How do we from a quality data 4.0 data science, how do we design AI assisted data analytics, build that into smart products, smart services, so that they can account for the variance components of distributed, massively horizontally, vertically distributed manufacturing. So that again, thank you.
Great. Do you want to give your email that people want to?
Email is easy. tcotter, TCOTTER @odu.edu.
Okay. In case someone does want to give some feedback.
Yeah,
I did
I'm
put that,
again interested. This is research that I've been developing for a number of years as part of what I call cyber technical socio quality systems design for Industry 4.0.
Okay, well, thank you very much.
Thank you.
Appreciate the talk today, and hope everyone had a good time, and hope to see you in another webinar soon. Thanks.